Alright, welcome back, Digital Electronics. We are in Unit 2, Lesson 1, going through AOI logic implementation. Alright, so what we're doing in this one, we are going to be taking the circuit, alright, what we did before is we took a circuit, alright, we made a table, and we made an expression. Now we're going to take an expression, alright, and build the circuit off of it. So I'm going to give you a schematic. You're going to create the SOP, the sum of products logic expression, or we can also build it from a POS, a product of sums logic expression. Okay, so the first one, all right, a sum of products is going to end with an or. Anything that's a product of sums ends in an and. So that should give you a little bit of a shortcut there when you're doing it. So when we take this, okay, we want to implement each minterm in the logic expression with an AND gate with the same number of inputs. So what we're going to do, we're going to restrict everything to 2 input AND gates, okay, for the most part, because if I have you breadboard it, everything has to be done with 2 input AND gates, 2 input OR gates, because I don't have 3 input AND gates or OR gates for chips in class, okay? So just know that we're going to have to do that aspect. Alright, so here's what we're going to do. I'm going to give you this logic expression. F subscript 2 is equal to not A and B, not C and D, or B, C, not D, or A and not B. Notice I can say it a little bit differently. Anytime I'm ANDing something, it looks like we're multiplying, right? It looks like we're multiplying not A and B and not C and D. Or I could have said A bar, B, C bar, D. It doesn't matter, it means the same thing. The not and the bar means the same thing. So we want to go through this. So how many inputs do we have? That's the most important part. There are 4 different inputs, right? There's an A, B, C, and a D. And it looks like some of them are getting inverted, if not all of them are getting inverted. So we know we're going to need an inverter for each letter, okay? And we're going to need 4 inputs. So we start by drawing 4 inputs and we send each one into an inverter. All right, and then we know that we need at least how many OR gates there? 2 for sure, right? Because there's 2 plus signs. And then we need a third one that's a final one that ties them all together. Okay, so in this scenario, we're using multiple input OR gates. Okay, when I'm talking to you about why we need 2 and then the third one is if we were breadboarding, because we would only have 2 input OR gates and that would restrict us. Okay, but in this scenario, when we're doing these, and if you do it in multi-sim or I give you multiple choice, it will be okay to choose the multiple input AND gates or OR gates. Alright, but just know everything we're going to breadboard is in 2. So what did we do? We have a 4 input AND gate. If we take a look at the 4 input AND gate, alright, what's going in there? Not A, B, not C, and D. So we can look at where those connections are being made. Then we have a 3 input AND gate that has B, C, and not D going into it. And then the last AND gate has A and not B, and then we have to OR all of those together. Okay, so those are all of our viable options. You're going to make a bus like this with A, B, C, and D. I'll show you how in multi-sim that you're going to use to do all of your logic operations. Alright, so that's one thing that we're going to, I'll walk you through. I'll have a video that shows how I want you to make a bus too. Okay, or I just might have it up there. You guys know where all the parts and pieces are and things like that. But I want to show you what I need. And you'll start all of your, you don't have to redraw it, you'll start everything, all your problems out this. Okay? So we have to take that same circuit. So like I was saying, if I asked you to breadboard this same circuit, this is the original circuit right here, okay, with multiple input AND gates and OR gates. Now, like I said in class, we only have 2 input and OR gates I'm going to have you breadboard with. I might have some 3 input ones, but I'm pretty positive I don't right now. But this is how this circuit would change. We would have to have more logic gates. So it would take 2 AND gates alone, as you can see here, to make the first expression. Not A and B, not C and D. So that requires 2 AND gates and then a third AND gate to take those 2 expressions and push them together. Okay, so you can see what a difference it's going to be electronically if we have to use 2 input AND gates versus a 4-input AND gate, which is much more convenient. All right, and then look, instead of having one 3-input OR, we have to have 2 sets of ORs, okay? Because we're going to OR one chunk together, and then we can OR the last chunk together to get the expression. So what you might want to do is draw both these circuits out and see what the changes are. Draw this first circuit out, that's a solution, and draw the second circuit out, that's a solution, and kind of see how it takes 3 AND gates to make one 4-input AND gate, and then see how it takes 2 different OR gates to make a 3-input OR gate. Okay, and be able to compare the two with the expressions. Okay, so what we just did was a sum of products. Now we're going to do a product of sums. So you're going to have a bunch more OR gates and then an AND gate versus this one right here. This is a sum of products. So we're going to have more AND gates than OR gates. All right, because we're going to have more products that we're going to add together here. All right, when it's a product of sums, POS, all right, we will have more OR gates and then AND at the end. Okay, so important that we understand this. So in the expression looks differently, right? Look at what we have. We have W or not X or not Y or Z. All right, everything in that parentheses gets ANDed with the middle term there that's not W or X or not Y. And that also gets ANDed with the last expression, W or not Z. Okay, so notice product of sums. Everything in the parentheses is the sums. The parentheses, just like in math, represent multiplication. So hence we have product of sums as we go through this. All right, so we have to get all the sums. And first of all, how many variables do we have? We have W, X, Y, and Z. So we have 4 variables going on. And then we have to check, are we using an inverter on one? Well, there's a not W, there's a not X, there's a not Y, and a not Z. So yes, every single one of those inputs also has an inverter. Okay, so we're going to invert all the signals too. So when we draw this one out, remember this is using multiple input OR gates. So the first input OR gate that has 4 has the W or not X or not Y or Z. The middle one has not W or X or not Y. And then the last one has the W or Z. And then we can use a 3-input AND gate to multiply, in essence, right? Product of sums. Remember, product means to multiply in math, to put them all together. Okay? Now, just like with the other one, we have to simplify it based on if I ask you to breadboard this circuit down to this. Okay? So once again, the 4-input OR gate takes 3 OR gates to accomplish this. Okay? When we do this and the 3-input OR gate takes 2 OR gates to accomplish it. So you can kind of see, and then we do have the 3-input AND gate like it says here, but if it didn't, we would need 2 more AND gates to complete the last AND if we were breadboarding. So just like with the other one, go back, draw this circuit out. I think it's very easy for you guys to go from the expression to the circuit, okay? But what I want you to make sure that you know how to see is to go from this circuit that has multiple input gates, so like that 4-input AND gate, the 4-input OR gate, or the 3-input AND gate, I'm going to start that one over. The 4-input OR gate as well as the 3-input OR gate and how it translates to this circuit right here. Okay, how we replace it because we only have 2 inputs and how we force those through. Okay, I'll probably cover this one a little bit more in class. We'll get through some of these extensively, and then I'm going to have you breadboard them and create the truth table and then verify that the truth table matches your circuit, which matches the expression, which works exactly when you breadboard it out. So it's, the whole design process from beginning to end, starting with, most of the time we start with the truth table because we have a concept, right? Kind of like the majority vote we're going to do. We have a concept that we have to design. So we create a truth table, which tells us when we want the midterms, and then from there, all right, we create the circuit. All right, this is just going the other way. We have the expression, we're making the circuit. Okay, you're going to do some of this in multi-sim, to verify that it's working as well. But think you guys are getting the gist on this. So as usual, all right, email me with any questions, or if you're in class, right, ask me some questions, see if there's any problems we need to go over. All right, but that's AOI implementation. Okay, we did sum of products and product of sums. All right, guys, have a great day. I'll see you in class.